Hello, in this video we will go over um, inner product length and orthogonality. So this is linear algebra, and yeah, we're going to go over inner product length and orthogonality. So uh, inner product length and I can't even say that word, ortho orthogonality, an important tool for using. So it's basically an important tool for working with vectors in Rn is the dot product, or more generally, the inner product. The algebraic definition of the dot product in Rn is to multiply the corresponding components and add. So you probably learned this before in the previous linear algebra videos. So when you multiply two vectors, they got to be the same, right? They got to be the same length, the width, same column, same width. Um, Basically, you just multiply it out, right? Right? They have to be the same size, and you just multiply it out. Wait, actually, take that back. Remember, they don't have to be the same size. They just have to have the same. So if mn times n, okay, these two numbers has to be the same. Okay. When you multiply vector u times vector v, it's also the same thing as vector u transpose times vector v. So yeah, that's another cool thing to know about. You can multiply two vectors. What you could do is to make your life easier, you can transpose the first vector and multiply it by the second vector, and you'll get the same results. So some important facts about the dot products, or also known as the inner product. Um, if you multiply two vectors, it's actually the same thing as the magnitude of that vector squared, right? So for example, if you have vector u times vector u, it's the same thing as the magnitude of vector u squared, where the magnitude of u denotes the length or the norm of vector u. And when I say length, I mean the magnitude, right? Um, Also, if you multiply two vectors, you can switch the orders around. For example, vector u times vector v is the same. You would give you the same results as vector v times vector u. Here's an example. So if you look at vector v, you probably learned this from either pre-cal or trig. Vector v has a vector or a direction of 3 comma 4. So if you plot the point 3, 3 is like your x, 4 is like your y, you're going to get this vector, and you got to find this magnitude, which is basically the magnitude of v, which is the square root of uh, x squared plus y squared, or 3 squared plus 4 squared. And when you do that, you get 5. So this entire magnitude is 5. So that's a little bit of a review. Yeah, let's do an example. So let's say we are given three vectors. Vector u is this what is this? One, two, three. One, two, three, four. 4 by 1 matrix. And vector v is this also 4 by 1. And vector w is also this 4 by 1. What they want you to do is do some multiplication. So what would be vector v times vector w? Um, can we multiply those two vectors out? Vector v is 4 by 1, and then vector w is also 4 by 1. Isn't there a rule? Uh, so yeah, it looks like you couldn't, because this is what, a 4 by 1 matrix? Vector v is a 4 by 1, right? One, two, three, 4 rows in one column. And vector W is also a 4 by 1. And you're probably thinking, well, I can't multiply these two vectors because this has to be the same with this. Um, did you also know you can rewrite vector V times vector W? It's the same thing as vector V transpose times vector W. So it's still possible. So what is vector V transposed? So basically what you're doing is, here, let me show you. Vector V is this matrix, this vector, -1, 0, 2, 5. Vector W is this matrix, 4, -3, 0, 6, right? And all you're doing is, I guess you could just multiply these two numbers. So -1 goes with 4, 0 goes with -3, 2 goes with 0, 5 goes to 6. So you just multiply these two numbers and then you add them, like the dot product, right? So this is going to equal to -1 times 4 plus 0 times -3 plus 2 times 0 plus 5 times 6. When you do the algebra, -1 times 4 is -4. Wait, -1 times 4 is, so this 0 times 0, 2 times 0 is 0, 5 times 6 is 30, and then -1 times 4 is -4, and you get 26. Okay, so vector V times vector W is 26. Okay, let's do question B. Okay, so go ahead and copy these three vectors because yeah, go ahead and pause and just copy these three vectors because there's a part B. Part B says find the magnitude of vector U. So the magnitude of vector U is the same thing as the square root of vector U times vector U, right? So that is going to be equal to the square root of 2 square plus -1 square plus 3 square plus 2 square. Okay. And when you do this together, you get 4 plus 1 plus 9 plus 4 equals the square root of 18. Okay, let's move on to C. Question C says, what is vector U times vector V minus vector W parentheses? So this is actually the same thing as vector U times vector V minus W. So let's do this part first. Then we can multiply by vector U. So vector U was -1, 0, 2, and 5, right? And then we got to subtract it by vector W, so it's going to be minus, and it's going to be 4, and then this is going to be 0 minus a -3, and then this is going to be -0, and then this is -6, right? So when you do the algebra, this is what you're going to get. You're going to get -5, 3, 2, -1. And then vector u is this 2, -1, 3, and 2. So if you multiply this out, you're going to get, here, let me write it here. You're going to get 2 times -5 plus -1 times 3 plus 3 times 2 plus 2 times -1. And when you do the work, you get -9. Okay. Question D says, unit vector in the direction of vector W. So they want to find a unit vector in the direction of vector W. So what that mean is this. And they're asking, unit vector is going to be vector W over magnitude of vector W, right? So let's do the bottom. What is the magnitude of vector W? That is going to be the square root of 4 square plus -3 square, 0 square, plus 6 square. And the vector W that was given, you can just write it as 4, -3, 0, and 6. Our unit vector is going to be 4, -3, 0, and 6. And then on the bottom, it's going to be the square root. What's 4 squared plus -3 squared plus 0 squared plus 6 squared? That is square root of 61. So you can also rewrite this as this is an invisible one. You can factor out this 1 over square root of 61. And I don't think 6 square root of 61 can be broken down. I think its premise can be. And then you're still left with this vector. It's going to be 4, -3, 0, and 6. So I guess this could be your final answer. Okay. Okay, let's move on to a next topic. So let's talk about distance in Rn. The distance between u and v is distance of u comma v, which is equal to the magnitude of u minus v. So this agrees with the usual formulas of r squared and r3. Let u equals u1 comma u2 and v equals v1 comma v2. Then vector u minus vector v is the same thing as u1 minus v1 comma u2 minus v2. So you kind of remember this in, what is it, either pre-cal or one of the previous linear algebra videos. When you're subtracting two vectors, they must be the same. Um, and the distance of vector u comma vector v is the same thing as the magnitude of u minus v, right? I kind of like show you an image, right? The After plotting those vectors, you have like a little line and you find the magnitude. That's the same thing here. So it's equal to the square root of u1 minus v1 squared plus u2 minus v2 squared. Or you could think of it as a square root of v1. This is also right. I won't get you a wrong answer. It's also the same thing as square root of v1 minus u1 squared plus v2 minus u2 squared. Okay, so let's do an example. find the distance between the two vectors. Okay, so you have these two vectors. Find the distance. Okay, so the distance is going to equal to this number minus this number squared. So it's going to be 1 minus minus 2 squared plus 3 minus 1 squared plus -3 minus 0 squared plus 4 minus 4 squared plus 0 minus 3 squared. And when you do the algebra, this is what you're going to get. You're going to get the square root. Two negatives become positive, so that's positive 3 squared. 3 minus 1 is 2 squared. -3 minus 0 is -3 squared. 4 minus 4 is 0 squared. 0 minus 3 is -3 squared. Keep on going. Oops. And when you do keep on going, you're gonna get 9 plus 4 plus 9 plus 0 plus 9. And you get square root of 31. Okay, so this is your final answer. Okay, so let's move on. Orthogonal vectors. So orthogonal vectors from geometry. Let's talk about orthogonal vectors. So from geometry, we know that two lines are perpendicular if and only if the distance from u to v from vector u to v is the same from vector u to minus v, which means that the squares of the distance is the same. So orthogonal means like some kind of perpendicular line or a 90-degree angle. Um, Remember in linear algebra, orthogonal means if you multiply two slopes, it gives you a product of -1. In linear algebra, it means the distance from u vector u to v is the same from the vector u minus v, which means the squares of the distance is the same. Right? So basically, if you find the magnitude of u plus v, it should equal to the magnitude of u minus v. So that's what orthogonal means in linear algebra. Uh, perpendicular is the same thing as orthogonal. And also, if you multiply, this is another way you can tell if two vectors are orthogonal. If you multiply out the two vectors and it gives you a product of 0, then you are perpendicular or orthogonal. Okay, as you can see, we're gonna also review law of cosines. We're gonna need this when we do the other problems. So if you recall, one of the form of a law of cosine is c squared equals a squared plus b squared minus 2ab times cosine theta. Um, Vectorized form from the law of cosine is this. Go ahead and write this down. Vectorized form for the law of cosine is this. Um, Basically, the magnitude of u minus v squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times magnitude of u times magnitude of v times cosine theta. Um, And then orthogonal vectors is the same thing as the distance of vector u, comma vector v squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times vector u times vector v. Okay, so let's do an example. So this example says determine whether the given vectors are orthogonal or perpendicular. So you're given this vector u, -1, 3, 2, and vector v, 4, 2, -1, right? We got to determine if it's orthogonal. So how do we do this? Well, you can multiply out the two vectors, and if it gives you a product of 0, then yes, they are orthogonal. So let's do that. So vector u times vector v is equal to -1 times 4 plus 3 times 2 plus 2 times -1, right? So -1 times 4 is -4, 3 times 2 is 6, 2 times -1 is -2, and it does give you a product of 0, so yes, it is definitely perpendicular. Okay, what about part B. Vector u is this and vector v is that. Are they orthogonal? So let's see. So let's multiply out the two vectors. And you get 0 times 5 plus 3 times 2, -2 times -1 plus 1 times 0 equals to 0 plus 6 plus 2 plus 0. That gives you 8. Unfortunately, that doesn't give you 0, so it's not orthogonal. Okay, let's move on to C. So vector u is this, and vector v is that. Are these orthogonal or perpendicular? Let's multiply out the two vectors. So it's -3 times 1 plus 7 times -8. Gives you -3 minus 56 plus 60 plus 0. That gives you 1, which does not equal to 0, so it's not orthogonal. What about D? Are these two vectors perpendicular? So let's see. Vector x times vector y is going to give you 12 times 2 plus 3 times -3 plus -5 times 3. That gives you 24 minus 9 minus 15. And yes, it does give you 0, which is orthogonal. Okay, now let's talk about orthogonal complements. So what is orthogonal complements? So let W be a set of vectors in an inner product space V. The orthogonal complement W raised W perpendicular to W is a set of vectors in V orthogonal to all vectors in W. What does that mean? So the orthogonal complement to vector this vector this vector 1, 2, 3 and R space on 3D space is a set of all x1, x2, x3 such that 1x1 plus 2x2 plus 3x3 is equal to 0. Okay, let's do an example. So let W equals span of vector U, which equals 1, 1, 0, 2, and vector V is 2, 1, 1, and vector Q is 1, negative 1, 1, and negative 1. Find the basis for W perpendicular, or find W raised to the perpendicular, which equals the null space of the matrix. So we got to find this. Okay, so how do we do this problem? Um, so A equals, so what we got to find matrix A first. So it's basically the mixture of vector U, Q, and U, V, and Q, which is 1, 2, 1, 1, 0, negative 1, 0, 1, 1, 2, 1, negative 1. This is x1, x2, x3, x4. So basically, because 1x1 plus x2 plus 2x4 equals 0. And then this row here is going to be 2x1, and then there's no x2, plus 1x cubed plus x4 equals 0. So what we're going to do with this matrix is row reduce, or set it augmented to 0 and then row reduce. So let's do that. We're going to put this in augmented to 0. It'd be 1, 2, 1, 1, 0, negative 1, 0, 1, 1, 2, 1, and then augmented with 0, 0. Then I'm going to use a calculator to row reduce it, and when I do that, I get this matrix. 1, 0, 0, 0, 1, 0, 1 half, negative 1 half, 0, 1 half, 3 halves, 0, augmented 0, 0, 0. So let me just write, oops. So let me rewrite what we just did. We basically we took our matrix A and then we augmented to 0 and then we wrote it reduce. So step 1. So the question says, what was the vector w raised to the perpendicular, raised to the perp? So w raised to the perp is equal to, so basically when you do this, this is x1, x2, x3, x4. Um, we know that one, sorry, yeah, one, this is 1x1. Hold on. So what, so it's going to be 1x1 plus 0x2 plus 1/2 x3 plus 1/2 x4 equals 0. And then this is going to be 0x1 plus 1x2 minus 1/2 x3 plus 3/2 x4 equals 0. And when you solve for it, solve for x1, x2, x3, you're going to get these two vectors. The first one is going to be negative 1/2, 1/2, 1 and 0. And then the second vector is going to be this negative 1/2, negative 3/2, 0 and 1. Okay, so let's talk about more inform definition. Uh, Continuation on orthogonal complements. Orthogonal complements and the row null and the column space, let A be an m by n matrix. Then the orthogonal complement of the row space of A is the null space of A, and the orthogonal complement of the column space of A is a null space of A transpose. So basis for W to the perp is equal to the null of A, and the row of A raised to the perp is also equal to the null of A. Go ahead and write this down. And then the column of A raised to the perp is equal to the null of A transpose. Um, what does that mean? So we have to, this is why we do examples. Okay, so let's say you had this matrix, this 2 by 3 matrix, right? 1, -2, 0, 0, -1, 2. And let's say we augmented to 0 and then we did some row reducing, and thus you get this matrix, such that column of A is 1, -2, right? And then the row of A is 1, 0, -1, right? And then null of A is null of A is 0, 1, 0, and 1, 0, 1. Okay. So I think this was all given, right? You have this matrix augmented with 0, and then we know that column A is 1, -2, and row of A is 1, 0, -1, and then the null of A is 0, 1, 0, 1, 0, 1. That was all given. They're asking you, is the null of A line or plane, is it in 2 space or 3 space? So what we got to do is figure out how many components are there. So here's the null of A, right? So what we got to do is figure out how many components. are there? Okay, so the null of A is equal to 0, 1, 0, comma 1, 1, 0, 1. That was given. There are three elements, right? Three elements, so we are in R space, 3D, right? You have 1, 0, 1. Okay, so that was question A. So basically, you count how many components you have. We have three. So we are in 3D, 3 space. Part B says, is row A a line or plane in are two space or three space? So in uh, row A was what? Row A was this matrix. 1, 0, -1. Um, it's a line, but there's three elements. So it's technically it is a line, but three elements. Or R cubed. Okay, what about C? C says, is column A a line or a plane in two space or three space? So if you recall, here's column A. There's two, right? There's two components. It's a line, but there's two elements, so that we are in 2D. Okay, last question. Question D says, find the basis for the null A transpose and determine if null A transpose is a line or plane in two space or three space. So null of A transpose was given, null of A T, it was -2, 1. We have a line and we have two components, so we are in two space. So it is in 2D. So we have a line and have two components. So we are in R2. Okay, that is answer D. Okay, so we're going to stop here, and then I think the next video will be linear algebra orthogonal sets. So yeah, we'll continue on orthogonal sets. So I'm going to stop right here.